So this is going on page 100 when we are done. We have been looking at trig functions. We talked about secant, cotangent a little tiny bit early on, and we haven't looked at them much. So we're going to look at the graphs and how to solve the equations with them and whatnot. If you know sine, cosine, and tangent, you can do these. Just like with the unit circle, we relate everything to the first quadrant. We're going to relate all the secant, cosecant, cotangent stuff to sine, cosine, and tangent, which we already know. So it makes it not that big of a deal at all. All right, so cosecant is what is the cosecant the reciprocal of? Sine, cosine, or tangent? Sine, right? Because there's only one co in each pair. So my function here would be f of x equals cosecant of x, and that makes it 1 over sine of x, right? And then we're going to draw our parent function that we're going to draw is sine, because again, we're going to relate everything back to sine, cosine, and tangent. We know what that parent function looks like. It looks like this, okay? And then we're going to use that to understand what's going on with cosecant. So we're going to first go over here to our little graph, and we're going to plot the points that we would plot for sine. So this here is at 0, 0. We're going to plot that point right there. And then what's the period for sine? 2 pi. So that means I'm going to put a point here at 2 pi. Okay, so 1 at 0, 1 at 2 pi. Then everything is half, 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 right? So halfway between these two, I have a point right here at 0. Halfway between these two zeros, I have a maximum at what? 1. So halfway between these two, which would be at pi halves, I go to 1. Halfway between these two, I have a minimum at what? -1. So halfway between these two, go to -1. Okay. Then, and since you have a pencil, you're going to sketch lightly, right? The only way I can do it lightly is with a light color up here. And we're just going to sketch lightly what the sine function is. So when we're done, this will kind of be the background is the idea. So just kind of lightly, so you can kind of see it, but it's not like we're graphing it, okay? Then we're going to use that to figure out what's going on with cosecant, right? So here, where sine is 0, cosecant is the reciprocal of that. What is the reciprocal of 0? The reciprocal of 0 is not 0. Smack yourself in the face. 1? Oh my God. All right. So 0 is 0 over 1. When you take the reciprocal, that is 1 over 0, which is neither 1 nor 0. It is what? Undefined. Thank you very much. You said that. Finally, I got that out of somebody. All right. So here, when sine is 0, cosecant is undefined. How do we graph undefined with these? What do we graph? A vertical asymptote. So we're going to have a vertical asymptote here at 0. It's actually every time sine is 0, we have a vertical asymptote. Okay? So I took care of all 3 of these. Those were asymptotes, right? Then halfway between these two, I would be at 1 for sine. What is the reciprocal of 1? 1. Halfway between these two, I'm at -1 for sine. What's the reciprocal of -1? -1. Okay. Then so this is pi halves. At pi fourths, what is the sine of pi fourths? Square root of 2 over 2. Okay, so square root of 2 over 2, which we would plot right about there. The reciprocal of that in decimal form, just so we can plot it here. It's not a value you have to actually know, and we're only going to plot it on part of this just so we can get an idea of what's going on. But the reciprocal of the square root of 2 over 2 in decimal form is about 1.4. So at pi fourths, we're going to plot about 1.4. So this is 0, pi fourths, pi halves. This would be 3 pi fourths. What's the sign of 3 pi fourths? Square root of 2 over 2. So the reciprocal is going to give me the same thing, right? Then when I get to 5 pi fourths, that's negative square root of 2 over 2, so it's about a negative 1.4. Same thing for this one. So that gives you an idea of what is going on with cosecant. Now it looks like little v's, but they can't be v's because we can't poke through the vertical asymptotes, right? So I have to hug those asymptotes as I go. So what's really happening is this. They look like parabolas. They are not parabolas because parabolas have a domain of all real numbers, but they have kind of that shape. I mean, that's at least what you think about when you see them, I'm sure. Looks like that. Okay, so it's kind of like we took sine and turned it inside out. That's the way I think about it. Now, just like the rest of them, they are periodic, so we can excuse me, we can continue this. So I have an asymptote here at 0, and then it happens every pi units, right? So that means going this way, I would have one at negative pi and one at negative 2 pi. And then if I'm going to the left, sine would be going down here to negative 1, then back up to 1. And like I said, we're not gonna worry about plotting those 1.4. I just wanted you to see what was happening. You can just draw these in because we're not gonna actually have to graph pretty ones too often. You just kind of need to know the shape and how the graph gets affected. That's way more important. So really just getting those points to be able to know the shape, we're good. Okay? What questions you got? We good so far? Okay. So then let's move on to secant. What is secant the reciprocal of? Sine. So is it the reciprocal of sine? Wasn't cosecant the reciprocal of sine? It's cosine. So f of x equals secant x is my function. That gives me 1 over cosine x. So I'm going to graph my cosine function, and it looks like this, right? All right, so here's some things, or actually, let's go over here, and we're going to do the same thing we did before. We're going to get cosine in the background. So at 0, I'm going to be at 1. At 1. So that's this one. Then I'm going to go to 2 pi, because that's the end of the period, and that's at 1. Halfway between the two, I'm at a minimum of negative 1. And then halfway between each one of those, I have a 0. So then we can just sketch in cosine so it's in the background there. So just like with sine, or just like with cosecant rather, secant is going to have asymptotes everywhere cosine is 0. So I can put in an asymptote here and here. And I know that the other points that I plotted are at 1 and negative 1, and the reciprocals are respectively 1 and negative 1. So I'm going to plot these points here. And then can I actually continue the rest of the graph on the left side before I even sketch stuff in? Because once again, the asymptotes are happening every pi units, but this is at pi halves and 3 pi halves. So over here I'm going to be at negative pi halves and negative 3 pi halves. And then I'm just going to alternate the 1 and the negative 1. And if we wanted to plot other points in there, we could, but we don't need to because, again, we're just trying to get the general shape of what's happening. And this is what it would look like. Oops. And it looks almost identical to cosecant, right? Which shouldn't be any big surprise because sine and cosine look almost identical. It's just a shift, right? Same thing for secant and cosecant. It's just a shift over. What questions do you have? Okay. Let's look at cotangent. What is cotangent the reciprocal of? Tangent. So f of x equals cotangent x. That would be 1 over tangent x. And then we're going to sketch in the parent function. Okay, so our parent function for tangent looks like this. Right. So if I'm going to plot that over here, I start at 0. I'll put a point there. What is the period for tangent? Pi. So pi is where I'm going to put that point right there. Okay. Halfway in between the two, I have an asymptote. Now I'm just going to sketch lightly like a little short asymptote right here just to, because I don't want it to confuse everything else that we do. You just kind of say, hey, I had an asymptote there, right? And then halfway between these two, we went up how much? 1. So halfway between these two, we were at 1, and halfway between these two, we were at -1. Okay? And then I could sketch, then we can sketch tangent in lightly again, kind of like this, where it's in the background, right? Just kind of lightly. All right. So now let's think about what we got here. When tangent is 0, what is cotangent? It's the reciprocal. What is the reciprocal of 0? Undefined. Thank you. I want everybody to say it. What is the reciprocal of 0? Undefined. Thank you. Okay. So I've got one there, and I've got one here. Because that's where my 2 zeros for tangent were, right? Okay, so then here I'm at 1. What's the reciprocal of 1? 1. What's the reciprocal of -1? -1. Okay, now here's where things might get a little tricky. Just verbiage. This right here for tangent at pi halves is undefined. The reciprocal of undefined is undefined because you can't take the reciprocal of anything that's not defined. Does that make sense to you? Like, technically that's what's happening. But the reason that we get undefined is because we are taking y over x and we put 1 over 0, and then that makes it undefined. When we're not doing that, we're doing the reciprocal of that then would be 0 over 1, and what does this give me? 0, right? So the reciprocal of undefined is not 0. Like, you can't say that sentence, it doesn't make any sense, okay? But on the graph, where it was undefined is now 0. So I know it's kind of contradictory what I'm saying. We do get 0 there because we're taking the reciprocal of these things. 1 over 0, the reciprocal is 0 over 1. But I can't say, like, 1 over undefined doesn't make any sense. This is the point I'm getting at. So wherever you have a 0, you have an asymptote in the reciprocal. If you have an asymptote, you have a 0 in the reciprocal. So by having this, cotangent looks like this. It looks very similar to tangent, right? But it's going the other way and it's shifted over. So can we continue this graph? Yes, we have an asymptote at every pi, right? So I'm going to have one at 2 pi. I'm going to have one at negative pi. I'm going to have one at negative 2 pi. Then I'm going to have zeros here, and here, and here. And then you should be able to fill out the rest just by repeating. What questions do you have? All right, well, while you finish up that graph, I'm going to pass out your next set of notes. I didn't want you to pick these up because I didn't want you seeing these graphs before we created them. Okay, put that away, Anthony, or I'm going to take it and shred it, and you're going to be sad. You put that away, or I'm going to take it and shred it, and you're going to be sad. Okie dokie. This, nope. This, nope. Come on now. There we go. All right, this is going on page 101, because that other little half sheet you can just tape in like flat, and then this will go on the next ones. All right, so this says we got 3 new functions that aren't very new, but we're going to relate them to sine, cosine, and tangent. That's what all those words say. Then here's our reciprocal functions, which we just talked about. Secant is the reciprocal of cosine, and secant, where cosine is not 0, and the graphs will each have vertical asymptotes whenever the denominator is 0, right? That's kind of basically what we just looked at with all those. One thing I want to add here, though, so we have cotangent is 1 over tangent. We just wrote that. That's true. But cotangent is also cosine over sine because we know that tangent x is equal to sine x over cosine x. So if I take the reciprocal of that, that gives me cosine over sine. So depending on how we are using it, we may want to write it this way or we may want to write it this way. Right now we're looking at it like this. Next week we're going to look at it some like this. So just throwing that out there while we introduce it. Okay, we good on that? All right, so then look, here are our graphs, which is basically what you just created and drew. But, and they have the sine and cosine like in the background also. That's not actually part of the graph, just so you know. Like if you graphed it, you're not going to see the little sine and cosine curves. It's just helping you see, again, like it's turned inside out. Okay. All right, so we have an infinite number of vertical asymptotes, and they're at specific places. So for secant is the reciprocal of what? Cosine. So secant has vertical asymptotes where cosine x equals 0. And so that would be the first time we have one. This is pi, which means this is at pi halves. So I have it at pi halves, but that's just one. They happen every pi units, so I have to say it's pi halves plus pi times k. And then we have to say where k is an integer. Everybody okay with why it's plus pi times k? And k could be -1, k could be 0, you know. All right, so then for cosecant, we have vertical asymptotes where sine of x equals 0. Our first asymptote is actually at 0. So that would be 0 plus something, so I'm not even going to write the 0. It's basically would be 0 plus pi k, so it's just pi times k, where k is an integer. What questions you got? Okay. Then the ranges of secant and cosecant are both blank. Okay, so I'm just going to draw another little thing over here so we can talk about a couple of things. Let's see, I'll put asymptotes here, here, and here. Okay. Then we'll just do this. Okay, so this is basically what cosecant looks like, right? Just a quick little sketch of it. And the secant is just that shifted over. But my ranges that I'm looking for here, what are these values in the parent function? What would this y value be? 1, and this one is -1, right? So the range, is that x or y? Y. What is the smallest y value I could possibly have? -infinity, which is technically not a value, but yes, you're right. So I'm going to start at -infinity. I never include my infinities. Then am I going all the way to positive infinity? No. Where do I go to? -1. Do I include -1? Yes, because it is a point I can plot. Then I have a space, then I start back over where? At 1 and go to infinity. Okay. So let's talk about some things that affect the range. If I take this graph and I shift it left or right, is that going to affect my range? No. If I have a horizontal dilation where I stretch or shrink it, is that going to affect it? No. If I take the graph and I shift it up and down, will that affect the range? Yes, because that affects the y values, right? What if I took the graph and I had a vertical dilation and I stretched it or I shrunk it? Then do you think that'll affect it? It actually does, because like right now your A is 1. If I had like 2 cosecant of x, that is a vertical dilation of 2, right? And so it stretches it, and it stretches it away from on either side, up and down, away from the x-axis. So these numbers would actually be -2 and 2 then. Does that make sense? Because it gets stretched like that. So for a parabola, no, a vertical stretch does, well, no, I guess it does. Never mind. It does. Even on sine and cosine, it does. It affects the range. I'm about to just lie to you and say different things. It looks different, but it does affect the range. Okay, so let's think about those things. All right, so flip this over. Here is cotangent. All right, and we've already graphed it and we talked about it. We have vertical asymptotes where tangent of x equals 0. Okay, and that happens, or the first time I have an asymptote on cotangent is at 0. So I'm not going to put anything. And then they happen every how many units? Pi. So this also is just pi times k, where k is an integer. And so we have these little equations. And when we're asked questions about this stuff, we could use the little equations, but they're so similar yet different at times. The majority of you are just not going to know them. And if you're going to figure out if you know them correctly or not, you're going to think about the graphs. So we might as well just use the graphs. I think that's a way better way to do this. And I think it gives you a deeper understanding of the graphs. So basically, like we have been doing on a lot of things, we're going to just draw a quick little graph so that we can wrap our minds around what's happening. Okay? So let's look at this first one. We've got 3 secant of 2x. Okay, so I'm going to draw myself a little graph over here. Secant is the reciprocal of what? Cosine. Okay, so my cosine, I would have a point up here, down here, and like I can just get the points in even if I don't graph the whole thing, right? And then I know that I have asymptotes here. Oh, goodness, that's stupid. I have asymptotes here and here. We agree with that? Just kind of gets them in the right place. Then I know that for cosine, my period is 2 pi, but that's not what's happening here, right? And we're asked about vertical asymptotes. Does a vertical dilation affect where my asymptotes are? No. Okay, so I can ignore the 3. Does a horizontal dilation affect where my asymptotes are? Absolutely. Okay, and so we're going to use that B to figure out what the period is. So the period for secant and cosecant are the same for sine and cosine. So when I go to figure this out, what goes in the numerator? 2 pi, and what's going to go in the denominator? 2, right there, right? So that gives me pi. Everybody okay with that? So if I'm concerned with where my asymptotes are, I know that the period, which would end here, is at pi. Halfway, which would be right here, is pi halves, right? Halfway between 0 and pi halves is what? Pi fourths. Halfway between pi halves and pi is what? 3 pi fourths. And having that much of a knowledge, I could then figure out where any other asymptote was if my answer wasn't there. But it says, which of the following is a vertical asymptote? What's my answer? C, right here. That make sense? We just got it from understanding that graph. What questions you got? All right, let's do another one. This one is cosecant. Cosecant is the reciprocal of what? Sine. So instead of doing a full parent function, I can just do this, right? Just kind of get some dots there. And then I know, before I worry about anything else, that I have an asymptote here, here, and here. Because this question is asking me about asymptotes. Now when I look over here, what does this 4 do to my graph? It's not a stretch. It's a vertical translation. It's just at the front, not the back. And if they put it at the front, y'all have no idea what's going on. I could do -2 cosecant of pi times x plus 4, and you'd totally be like, oh, it's a vertical translation. You put it in the front, and I don't know what happens. But yeah, it's a vertical translation. Does that affect where my asymptotes are? No, so I don't care about him. This negative is going to reflect it. I don't really care about that either. This 2 is a vertical dilation. Do I care about him right now? No. This is the only part that's going to affect anything that I'm looking at for this question. I need the period. What goes in the numerator? 2 pi. And then in the denominator I get pi, which gives me 2. So the period is 2. This, I have a vertical asymptote at 0. I have 1 at 2, and I have 1 halfway, which is at 1. My answer is D. Okay? Way better than trying to figure out little equations every single time. Okay? What questions you got? All right. Let's look at this next one. All right, so this next one is a cosecant function. Cosecant is the reciprocal of what? Sine. So I'm going to do sine. All right, now this one is not asking me about the asymptotes. It's asking me about the range. Okay. So for the range, does my horizontal dilation affect my range? No, don't care about that guy right there. Is this going to affect my range? Yes. For the parent function, this point and this point, because this is what the graph looks like, right? This point and this point are at 1 and -1. Where are they going to be now? 3 and -3. So my answer is what? C. What questions do you have? Anything? Okay. All right, so now example 4, we've got cotangent. So my tangent parent function, I have a 0 here, a 0 here, and a little asymptote here, which means I know that I have actual asymptotes here and here. And we're being asked about asymptotes again. All right. So then, does the negative or the 5 affect my asymptotes? No, it's just this part, right? So I need the period. What goes in the numerator? No. Pi, because this is tangent. Pi, the denominator goes 2 pi. When I reduce that, do I get 2? No. Somebody usually does, but the answer is no. This is 1/2. So that means that I have an asymptote here at 0 and one at 1/2. And even if one of those wasn't the answer choice, I could then figure out some more either way if I had to. My answer is B. What questions do you have? Anything? All right, we got one more page of notes. It's just one side, and we're not even going to get to all of them. But the last question is a calculator question. We're going to save that for Monday, just in the interest of time. That's cool. All right. Here we go. So this will also go on page 101. This paragraph basically says we've already been solving equations. We're going to continue to solve them, and it's no big deal. There you go. There's the summary. Because basically, again, if you can do sine, cosine, and tangent, you can totally do these. So we have f of x, g of x. We want the x coordinates of the points of intersection, and we have a domain restriction. Okay? So we're going to start the exact same way. If I want the points of intersection, what do I do with these two equations? Set them equal to each other. So I get 4 cosecant x plus 3 equals 11. Then I solve the equation exactly like I've been solving equations since before we were in Algebra 1. So I'm going to subtract 3 from both sides. 4 cosecant of x equals what? 8. Then I divide, so cosecant of x is equal to 2. So we've gotten to the point where we have isolated the trig function, okay? I don't expect you to just know your cosecant and secant values because we're going to relate everything to sine, cosine, and tangent. So what is cosecant the reciprocal of? Sine. Okay, so if the cosecant of x is 2, then the sine of x has to be what? 1/2. And then from that, can you get values? Yes, I think you can, right? Sine is positive in the first and second quadrants. All right, so what angle gives me a sine value of 1/2? Pi 6. And then what is my other angle? Another angle. 5 pi 6. Everybody okay with that? If you can do the others, you can do these, right? You just got to get it to that point, and then you just flip it over. Okay. Example 6. We've got these two equations. I want the points of intersection. You got this domain restriction. You work on that one. Go check roll so I don't forget. So when you're done, check your answer with me, and then let me know if you have any questions. And while you're finishing up, because some of y'all are still working, and that's fine, I'm going to hand out the assignment. We're going to save this till Monday, and there's only one calculator question on the assignment, so you can totally do the rest of it.